Hello, Physics 30s. Today we are going to talk about our first lesson in Unit 5, the atomic physics unit. We are talking about photon theory, which is all about light still, which is pretty wild. We're talking about atoms, but we're talking about light. This is a really cool unit. I'm really excited to teach it to you here. So hang on to your seats. Okay, the first thing we want to talk about is getting into a little bit of quantum theory. Quantum theory sounds scary. It's looking at things at more of an individual level. That's all we're really doing when we talk about quantum theory, looking at individual pieces, so individual photons, individual electrons, things like that. Okay, so jumping in, at the end of the 19th century, most physicists believed that these were the big things that could explain everything in the universe. So Newton's 3 laws of motion and Maxwell's 4 laws of electromagnetism. Lots of people figured that this could explain every single little tiny bit of motion and thing in the entire universe. Problem is, though, blackbody radiation. This is where it all started off. And something important to note, we're not going into a ton of detail here because this is not actually part of your Physics 30 curriculum. That being said, if you want to check it out, if you want to learn a bit more, go wild. There's no one stopping you. So, blackbody radiation. First off, a blackbody is a metal that is normally black at regular temperatures, right? So here we've got a black body, no problem. A chunk of metal that is typically like blackish in color. Realistically, it's any metal, right? So like a black steel bar, a stove element is another place where we often see this. Doesn't give off light at room temperature, at least not light that we can see anyways. When you heat it up though, it starts to glow. So picture a hot stove element. It starts to glow and it starts to give off light, which is, you know, what we talked about last unit, electromagnetic radiation. So it gives off this radiation. We call it blackbody radiation because it's coming from something that should have been black, right? It should not be glowing red. It should not be giving off that light. Now, if we were to actually take a graph of the wavelength of that light versus the intensity of the light that's given off at a particular temperature, this is the pattern that we would see. So we see, obviously, at 5,000 degrees, I think that would probably be in Kelvin at that point. At 5,000 degrees Kelvin, a lot of the light and the highest intensity is for violet. Lots of it's red. Hey, there's our visible between violet and red. And then we get a little bit in IR, and then just this huge drop in ultraviolet and nothing really beyond ultraviolet. So interesting pattern. This pattern really doesn't fit the classical theory of EMR. And remember, the classical theory is treating light like a wave, like it's a true 100% wave. So again, this is the classical prediction. You really don't necessarily need to, at this point in your physics career, get into much more detail, other than the classical prediction should have looked like this green line that I now highlighted in blue. So it should be a nice, easy, inverse squared relationship with a classical relationship. It didn't happen, though. Max Planck is the person who figured this out for us. So here's a picture of Planck up there. Here is the equation to fit this graph. It is slightly more challenging, I suppose, this equation than our simple relationship. But big important things, and you don't need to know this entire equation, but this H, holy mackerel, that H, that lowercase h in there is just such an important little piece. So here's how Max described it. And this is where we should jump in and we should actually start to realize, and this is now Physics 30 material from here on in. So what Planck said was the atomic vibrational energy of an atom is quantized. Now again, there's that word. All it really means is it can only be in very, very, very specific places. So if this is our vibrational energy, and this is a little chart of our vibrational energy, you can have an atom vibrating with this amount of energy, with this amount of energy, with this amount of energy, but not with this amount of energy. So nothing in between, which is kind of interesting and, well, to be totally honest, very different from what we've seen before. I don't know why that felt pen got so thick. So it has to be at very, very particular places. Now, what you'll notice with this is that each of these energies is h times f, where h is Planck's constant. There it is. And we'll talk about that more in a bit. And F is the vibrational frequency. So it's Planck's constant times the frequency, and it's a whole number multiple of that frequency. Cool. Okay, so this doesn't really necessarily explain blackbody radiation yet, but we're getting there. So atoms only vibrate with very, very, very particular energies. Now here's the sort of thing that changes a little bit. So remember Maxwell's laws of electromagnetism essentially said that accelerating a charge equals EMR, right? So realistically, it doesn't matter what vibrational energy we're at. If it is vibrating back and forth, if an atom is vibrating back and forth, we should be giving off energy, right? We should be giving off EMR. But the vibrational energy at 3HF, so at the third energy level that we've got there, if it just sits at the third energy level, it's not actually giving off any energy. If it sits at the second, it's not giving off any energy. So if it's sitting there, nothing happens. Where the energy and the EMR is being given off, the electromagnetic radiation is given off, is when there are jumps between those energy levels. In particular, jumps down from those energy levels. So as we jump from 3HF to 2HF, so as we come downwards, a little packet of energy is being given off. That little packet of energy is what we call photons. And this leads us to photon theory, which is the next level of what we're talking about with light. So rather than light being a continuous wave, we're talking about light being a whole bunch of individual little tiny packets of energy called photons, which is pretty wild, pretty neat. Now, if we wanted to calculate the energy of a single photon, so of one single photon, we've got a couple formulas here. Well, it's realistically one formula. It's kind of rearranged a little bit. So we've got energy is equal to h times f, so Planck's constant times the frequency, and it's also equal to hc over lambda. So h times the speed of light divided by lambda. You can see if you can make that second formula from the first one using our universal wave equation. So that's essentially how we go from the first chunk of the formula to the second chunk of the formula. Realistically, they're on your data booklets, so you don't necessarily need to, or your data sheets, or you don't need to know how to get from one to the other. But if you're looking for a challenge, go for it. See if you can figure that one out. So F is frequency, lambda is wavelength, and H is Planck's constant. So cool, fairly straightforward so far. Nice. Let's just relate that to frequencies now, because we all remember, we are all in Unit 4. Remember that raging Martians invade Venus using X-ray guns, so we know the order of the EMR, and we know it from longest wavelength to shortest wavelength. We know it from lowest frequency to highest frequency. So can we relate the energy of a single photon to frequency and wavelength? So let's check this out. It is a direct relationship with frequency. So E has a direct relationship with frequency. So that means the higher the frequency, the higher the energy. That means high energy over here. What about wavelength? Energy has an inverse relationship with wavelength. So that means the shorter the wavelength, the higher the energy, which is still kind of over here. Perfect. Okay, so we should know those relationships. And typically, it's only those high frequency or short wavelength that have enough energy to be dangerous to our cells. Because is visible light dangerous to our cells and our bodies? Not really. Is infrared? I mean, it can burn you, so yeah, kinda. But which one really is ionizing radiation? Well, it's ultraviolet, it's X-ray, and it's gamma rays that can do some serious damage to individual cells. Cool. Let's check out a couple more things with this Planck's constant and a new way to measure energy. So energy from here on in could be measured in joules. Nice, and that's pretty standard, that's pretty usual, but we could also now measure it in electron volts. So 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. So if you ever hear electron volts, you know electron volts is a measure of energy, and you know that one of them is 1.6 times 10 to the negative 19. So we have a conversion factor to go back and forth. Again, you might want to check this out. This is on your data sheet. Something that lots of people might be thinking about. You're like, oh, 1 electron volt, 1.6 times 10 to the negative 19 joules. Hey, wait a second, 1.6 times 10 to the negative 19, that's a pretty familiar number. That's the charge of 1 electron, obviously with different units, right? 1.6 times 10 to the negative 19 coulombs. So that actually leads us to our definition of an electron volt, and it's the amount of work that's done, or the amount of energy that changes as one electron moves from one side of a parallel plate apparatus to the other side across 1 volt of potential difference. So it's the amount of work that's needed to push one electron across 1 volt of potential difference. So if we go back to unit 2 here, we've got voltage is equal to a change in energy per unit charge. So if I were looking for the change in energy, that'd be delta V times Q. Well, that's just 1 times Q, and Q in this case is realistically, let's get rid of that. So 1 volt, go back to the felt pen here. Sorry, folks, be patient with me. Is it skinny? It's skinny. So that is 1 volt, which remember 1 volt I'm going to change to 1 joule per coulomb, times the charge, 1.6 times 10 to the negative 19 coulombs. I kind of ran out of space there, my apologies, but coulombs cancel, and it is equal to 1.6 times 10 to the negative 19 joules. So by definition, 1 electron volt is the same thing as 1.6 times 10 to the negative 19 joules. Sorry about the mess in the side over there. Okay, so because there's 2 different ways to measure that energy, there are 2 different values for Planck's constant. There is 6.63 times 10 to the negative 34 joule seconds, or 4.14 times 10 to the negative 15 electron volt seconds. So be very careful, make sure you're showing your units, and make sure you're knowing which value of Planck's constant to use. Cool. So just a couple quick notes. Converting. If I wanted 340 electron volts and I wanted to turn that into joules, well, the way I would do this is I would set this up as a conversion factor. I want to cancel electron volts, so that goes on the bottom. I want to end up with joules, so that goes on the top. Nice, electron volts cancel. Now I know that it is 1.6 times 10 to the negative 19 joules for every 1 electron volt. If I were to multiply this out, we would get whatever 340 electron volts is in joules. Do I have a calculator handy? Let's just do that real fast here. 1.6, 10 to the negative 19 times 340. It's going to be a tiny number, 5.44 times 10 to the negative 17 joules. Cool, so that's not so bad. If you wanted to go the other way, it's realistically the same thing, except now the joules goes on the bottom, so we're still using our conversion factor, 2.1, dang it, 2.1 divided by, you know what, I'll let you do this one. I'm messing up in the calculator there, and I don't want to waste your time. But you can definitely try this one. This one should be probably in the range of maybe a couple hundred, I'd say, based on those values there. But test it out. Okay, so we've already got an example here. We've got, for the light wave shown, so because it's a light wave, we know a few things like its speed and stuff like that. Determine the total energy of 71 photons, and we want to answer in electron volts. And then we want to go ahead and convert our answer to joules, just because why not? We can get a bit of practice with this. Okay, so let's see what this thing is showing us. This thing is showing us, for the wavelength, it's showing the distance that it goes in nanometers. Or sorry, not the wavelength, but it's showing us the distance that goes in nanometers. And let's see, we've got 1, 2, and 3 wavelengths equal to 650 nanometers. I'm pretty sure we can figure out the wavelength from that. So let me get a nicer felt pen width. I guess we're using red now. So 3 wavelengths is equal to 650 nanometers. So let's see, I want 1 wavelength, so I'm going to divide both sides by 3. 650 divided by 3 should be 216.67 nanometers. Awesome, and that's a rounded answer, so we'll just make sure that we keep all those digits in till later on. So now we've got the wavelength. Okay, cool, and it says determine the total energy for 71 photons. Okay, well I think what I'm going to do now is I have the wavelength, and I've got the energy of each individual photon. So I'm writing EPH, that means for one photon, is going to be equal to H times F. Oh, well, that's not very useful. We don't really have the frequency. So maybe I'm going to go ahead and use the other one, HC over lambda. Okay, so I'm looking for that. I got H, I have C, and I now have lambda, so I think I'm good to go. Let's see, it says answer in electron volts. So if I wanted to answer this in electron volts, I'd go H, well that's 4.14 times 10 to the negative 15 electron volts. Shoot, that should say 15. It kind of looks weird there though. 15 electron volt seconds. There we go. So Planck's constant in electron volts times the speed of light, 3 times 10 to the power of 8 meters per second. And then we want to divide this by the wavelength. The wavelength we just said was 216.67. Oh, I almost wrote nanometers. We want to turn this into regular meters, so times 10 to the negative 9 regular plain old meters. Check out what happens here. Meters cancel with meters, seconds cancel with seconds. The only unit we have left is electron volts, which is perfect. That's what we want, electron volts. So take a second to plug that in your calculator and see what we end up with. Alrighty, so if you ended up with 5.732 electron volts, 5.732 electron volts, I think you are spot on. Perfect. Exactly what we're looking for. Does that answer our question, though? Not really, because that's the energy for one single photon. We want the energy for 71 of those photons. So if this is the energy for one photon and we want 71, all we have to do is multiply this by 71. So the total energy is going to be equal to 71 photons times the energy per photon, 5.732 electron volts. And when we plug that in, that then works out to be 407 electron volts. Cool. That's our total energy. And in doing this, you might not realize it, but we just built a formula similar to Q is equal to NE, right? So remember from unit 2, Q is equal to NE. Well, we're not dealing with charges, but what we are dealing with is the total energy is equal to the number of photons multiplied by the energy of each photon. And we can now use this super simple formula. We can rearrange it. We can do whatever we need to figure out, say, the total number of photons, the total energy from those photons, or the energy from each photon. Last thing the question asks us to do is just to figure out that total energy in joules. So I'm going to do 407 electron volts. I'm going to multiply it by my conversion factor. Electron volts goes on the bottom so that they cancel. Joules goes on the top, and it is 1.6 times 10 to the negative 19 joules for every 1 electron volt. You can put the video on pause, plug that into your calculator, and I'm doing the same thing. And turns out to be 6.51 times 10 to the negative 17 joules. Okay, I didn't really circle the answers, but there are my two answers, both in joules and in electron volts. Awesome, very, very cool, very neat stuff. Individual photons now. Okay, that was some space for me to work. That's more space for me to work. Next thing that we want to talk about here is what brightness really means, or intensity really means of EMR. So classical theory and quantum theory are very different in this respect. So remember, classical theory, we're treating it like a wave. And where do we get the energy from a wave, which would correspond to the brightness? If you're thinking the amplitude, oh, well, you are doing great here. So amplitude tells us about energy. For light, that would tell us about brightness. For EMR, it's going to be a little different. So again, here's a slightly better picture, and by slightly I mean considerably better picture of what I drew. So classical theory is all about amplitude. So bright light would have a high energy because it's got a high amplitude. Dim would have a lower energy and therefore a lower amplitude. Whereas classical theory, now this is a little bit different because each individual photon of the same frequency has the exact same energy. Right? So each individual photon. So what this now comes down to is how many of those photons do we have? So if I have really bright light, I have a large number of photons, potentially each with the same amount of energy. If I have dim light, it's now a smaller number of photons, again, with potentially the same amount of energy each if they're the same frequency and wavelength. Cool, so brightness is now about the number of photons that we have rather than the amplitude of those photons. Cool, so let's check out one more quick example here. So we have a 90-watt light bulb. Oh, we haven't dealt with that in a little while. What is 90 watts? If you're thinking to yourself, power, perfect, and we even have a formula for that. Power is equal to work or a change in energy per unit time. Cool. So let's see. It emits 1.2 times 10 to the power of 15 hertz or 250 nanometer UV rays. So this gives us both the frequency and the wavelength of those UV light rays. We want to determine the maximum number of photons emitted in 10 seconds. So this maximum, it's underlined, it must be kind of important. The maximum number of photons, all we're thinking about with that is we're assuming that the light is 100% efficient so that all 90 watts of power and the energy that corresponds to that that's going into the light bulb is coming out as light energy, not wasted as heat energy. So we're assuming that it's 100% efficient. So let's see, I think what we can do here, if we start to make a plan, so I want to figure out the number of photons, the maximum number of photons, and if I want to figure out the maximum number of photons, I'm probably going to need the total energy for those photons, and probably going to need the energy for each photon. So let's just think about that. Our total energy is equal to the number of photons times the energy of each photon. So I'm looking for the number of photons. I need to figure out the total energy, and I need to figure out the energy per photon. Okay, cool. We've got a plan. Let's try and figure out those two things. So back to a skinnier felt pen. There we go. And I'll be working in blue now. First off, my total energy. It's 100% efficient. So that means all of the energy that's going in is going to be turned into light energy or photon energy. So this change in energy is just going to be equal to my total energy. So I can rearrange this and I can say my total energy is equal to the power multiplied by the time. Well, that's just 90 watts multiplied by 10 seconds. I love this math. Look at this, 900 joules of energy. So that's my total energy. Awesome. Okay, so I got part of it. The next part of it is I need to go ahead and I need to figure out what the energy for each photon is. Okay, so let's see. I just learned a formula for that. Energy for the photon is equal to H times F, which is also equal to H times C over lambda. We have frequency and we have lambda. So I mean, we could use either of these. So you know what I'm going to do? I'm going to use the easier one. A little bit less math involved with this. So energy of each photon is equal to H times F. Now I got to be real careful here. My value for H, well, if my total energy is in joules, I probably want my individual photon energy to be in joules as well. So let's use the 6.63 times 10 to the negative 34 joule seconds. So Planck's constant with joules in it times the frequency. I forget what the frequency is. I got to go back up here. 1.2 times 10 to the power of 15 hertz. Cool. And you'll notice that, remember, hertz is an inverse of a second. So hertz actually cancels out with seconds. Perfect. All we've got left is joules. Nice. So you can take a second and plug that in. You can put it on pause if you need to. Go for it. For me, it works out to 7.956 times 10 to the negative 19 joules. Okay, cool. So we've got the total energy, We've got the energy of each photon. I think it's time to come back to this red formula. I'm just going to do it below so it's a little bit neater. Okay, I got the right felt pen. So last step here, we got the total energy is equal to the number of photons multiplied by the energy of each photon. So we want the number of photons, that's going to be equal to our total energy divided by the energy for each photon. So I got to get those numbers back here. That's 900 joules divided by the number that I got right up top there, 7.956 times 10 to the negative 19 joules. And number of photons doesn't have a unit, which is good because joules is canceling with joules. Would that have canceled if we had one of those two in electron volts? Not so much, right? So it's important to pay attention to those units. Take a second and plug that into your calculator. Go ahead, you can put it on pause right now if you need to. For me, turns out, and hopefully for you as well, 1.13 times 10 to the power of 21 photons. Now that kind of makes sense, right? Because the energy for one photon, if it's 10 to the negative 19 joules, we got 900 joules. It's going to be a ridiculous number of photons, like a very, very extremely large number of photons. So that is, oh, some space to work, just double checking. That is essentially our lesson for today, looking at the idea of photon theory, and this whole unit is kind of exploring with photon theory and with things behaving as individuals, so as quanta, which is getting into some kind of neat stuff. Anyways, that is it for now, Physics 30s. I will see you again soon. Bye-bye.